Solve the rational inequality algebraically. In this video, we're going to be using the boundary point method. In the boundary point method, the first thing that we want to do is make sure that we have 0 on one side of the inequality and a single put together rational expression on the other side. Then, in order to find the boundary points, we're going to look for the zeros of the numerator and the zeros of the denominator. In order to find the zeros of the numerator, we'll need to figure out who are the x values that cause the numerator to be equal to 0. The numerator is x squared minus 9, which is a quadratic that can be factored into x plus 3 times x minus 3. So we set each of these factors equal to 0 and solve for x to get the zeros of the numerator being x is equal to negative 3 and x is equal to positive 3. To get the zeros of the denominator, we'll do the same thing. We take the denominator, set it equal to 0, and solve for x. This quadratic factors into x plus 3 times x plus 2. And when we set each of these equal to 0, we get that the zeros of the denominator are negative 3 and negative 2. Now these zeros become the boundary points that we plot on a number line and then test values inside the resulting intervals. So these boundary points are going to be placed on the number line. We have negative 3, negative 2, and positive 3, and we'll be testing 4 intervals. We'll start down here with x is equal to negative 4. In here we don't have an integer that we can use, so let's use x is equal to negative 2.5. The value 0 is inside this interval, so let's use that. And above 3 we'll test a small integer quantity, let's say x is equal to 4. All of these test values are going to be used back in the original inequality to see whether or not they make a true statement. So we have x squared minus 9 in the top, and x squared plus 5x plus 6 in the denominator. We'll start by testing x is equal to negative 4, so negative 4 goes in for all the x values, and then we evaluate to see whether or not this is a true statement. In the numerator, we have positive 16 minus 9, which is 7, and in the denominator, negative 4 quantity squared is positive 16, minus 20 plus 6, which is positive 2. 7 halves is the output on the left-hand side, which is greater than or equal to 0, so that is a true statement, and therefore negative 4 is part of the solution set. So we move into the next interval now by testing negative 2.5. So negative 2.5 goes in for all these x values. Negative 2.5 squared here is going to be positive 6.25 minus 9 in the top. Again, we have positive 6.25 in this position. 5 times negative 2.5 is negative 12.5 plus 6. 6.25 minus 9 in the numerator is negative 2.75. And all of this in the denominator combines to be negative 0.25. And a negative number divided by a negative number is going to be a positive number greater than 0. So x is equal to negative 2.5 is also going to represent a working interval. Moving over to our next interval, represented by x is equal to 0, we plug 0 in for all the x values. In the numerator, that gives us negative 9, and in the denominator, that gives us positive 6. This ratio is going to be a negative quantity, which is not greater than 0. So the interval represented by x is equal to 0 is not going to be part of the solution set. Moving now to the last interval, represented by x is equal to 4, we plug 4 in for all the x values. Here we have positive 16 minus 9 again in the top, which is going to be 7. And then in the denominator, we have positive 16 plus 20 plus 6, which is 42. Now you can see that we have a positive number over a positive number, which is going to give us a value that is greater than or equal to 0. So the interval represented by x is equal to 4 is going to be part of the solution set. Now remember, we also still have to check the boundary points themselves. So we'll begin by testing x is equal to negative 3. When we plug negative 3 in for those x values, we get negative 3 quantity squared is positive 9, so 9 minus 9 in the numerator is 0. Notice also that we have positive 9 minus 15 plus 6, which is also 0. 0 over 0 is an undefined quantity, which means that this is not a true statement. Undefined is not greater than or equal to 0. So this boundary point, negative 3, is not part of the solution set. Now let's look at the boundary point x is equal to negative 2, so we'll plug negative 2 in for all the x values. In the numerator, we have positive 4 minus 9, which is negative 5. And in the denominator, we have positive 4 minus 10 plus 6, which is 0. Again, this quantity is undefined, which means that this is not a true statement, and negative 2 is not part of the solution set. We have one last value to check, and that is x is equal to 3. So we plug 3 in for all the x quantities to get positive 9 minus 9 in the numerator, which is 0. 9 plus 15 plus 6 is 30 in the denominator. When we have 0 in the numerator, this fraction is actually then equal to 0. So we have 0 is greater than or equal to 0, which is a true statement. So this boundary point is going to be included in the solution set. Now that we're finally done with all that testing, it's time to state our answer. This leftmost interval is part of the solution set, and it starts at negative infinity. So we begin at negative infinity, we always leave infinities out with a parenthesis, and we go up to the boundary point. Remember, the intervals stop and start with boundary points, not the test values. So we go all the way to the boundary point negative 3, but because negative 3 didn't work in the inequality, it's not going to be included in the solution set. Now we move over to the next interval, which also worked. But that interval begins with negative 3 again. So we're going to start with negative 3 and connect these two intervals with the union symbol. So beginning with negative 3 and ending at the next boundary point, which is negative 2. Again, negative 2 did not work, so we're going to leave that out with a parenthesis. We're going to skip over this next interval because this next interval did not work and move to the last interval, which did work. That interval begins with the boundary point of 3, but 3 was a boundary point that actually worked. So we are going to include positive 3 in the solution set. And this interval ends out at positive infinity, so we will close this up with a parenthesis. So this is the solution to that rational inequality, and now we're going to check our answer by graphing it. So here's the rational inequality, and we're going to graph it by taking this rational expression, setting it equal to y, and then using our processes for graphing a rational function. In order to graph a rational function, the first thing that we wanted to do was to factor the numerator and denominator completely. And when we do that, we see that we have a common factor of x plus 3 in the numerator and the denominator that cancels out. So this rational function actually simplifies down to being x minus 3 over x plus 2, but then we manually impose the domain restriction that was lost in that simplify step. And this domain restriction that we lost is going to be represented by a hole in the graph. Again, we're going to find the vertical asymptotes, horizontal asymptotes in this case, there are no obliques, the x-intercepts, the y-intercepts, and let's also make mention of the fact that there's a hole. The vertical asymptotes are going to occur at the zeros of the denominator, so x is equal to negative 2 is a domain restriction that on our graph is going to be represented by a vertical asymptote. The horizontal asymptotes are going to be represented by the ratio of the leading coefficients because the degree of the top and the bottom are the same. So the leading coefficients are 1 and 1, and their ratio 1 over 1 is just the quantity 1. So that's our horizontal asymptote. The x-intercepts occur at the zeros of the top. When x is equal to 3, the output of this rational function is going to be 0. The y-intercept occurs when the x-coordinate is 0, so when we plug 0 in for x here, we're going to get negative 3 over 2, which is negative 3 halves. And again, we said that the hole occurs at x is equal to negative 3. So let's sketch this rational function starting with the asymptotes. We have a vertical asymptote at x is equal to negative 2, a horizontal asymptote at y is equal to 1, an x-intercept at 3, 0. Remember, we always want to clearly label our graphs. The y-intercept is at 0, negative 3 halves, which is negative 1 1/2. And let's wait just a moment to illustrate the hole. This rational function has to connect in this way. It's got to approach the asymptotes and pass through the intercepts, and there's only one way for that to happen down here. The rest of the graph must happen up and over here because we don't have any additional intercepts to the left of negative 2. Now it's time to discuss the hole in the graph. The hole happens at x is equal to negative 3. So we find the x value -3 on the graph, which is happening somewhere up here, and essentially we just erase that little bit of the graph. So this is the graph of this rational function, and we want to determine where the output values of this rational expression are greater than or equal to 0. Well, those output values are represented by the y values on the rational function. So we want to know where these output y values are greater than or equal to 0. Well, that happens here. These ordered pairs have y values that are greater than or equal to 0. And these ordered pairs have y values that are greater than or equal to 0. But what about at x is equal to 3? The x value 3 causes the y value to be equal to 0, so 3 is part of the solution. And let's illustrate that by coloring in that dot. Now it's time to clearly state the solution set. The x values that cause the y values to be greater than 0 start way out here at -infinity and come all the way up to -3. Negative infinity, of course, gets a parenthesis, and when we come up to -3, we see that there's a hole in the graph there, which means that at -3, the y value does not exist. So since there's no graph at -3 is not part of the solution set. We then pick up at -3 on the other side and go up to -2. So starting with -3, again not including it, we do need to put the union symbol here. And then going up to -2, well, at -2, again, the graph does not exist there, so -2 could not possibly be part of the solution set. In this interval, the y values are negative. So from -2 to +3, that interval is not part of the solution set. Then we pick up at the 3 and go out to +infinity. The x value 3 generates a y value of 0, which is allowed, so 3 is included. Let's add the union symbol here, and then go off to +infinity, again with a parenthesis around the infinities. And now we can see that our solution is the same as what we had a moment ago.